So welcome to the second class of statistical modeling. We continue with the analysis of principal components. Yesterday we saw how to obtain these first principal component, or a set of principal components, that is a set of variables that are linear combination of the original variables, which explain as much as possible the variability of the data. That was our goal, and we saw the mathematics behind. Now, there is another approach of principal components that passes through the singular value decomposition. Have you already heard the singular value decomposition? Or never? Okay, now let me try to connect again. Right, okay. So the purpose is you have a matrix which is n times p, which has rank, for example, R, let us say. Well, you want to approximate these n times p numbers. So suppose that n is 1000 and p is 5, these 5000 numbers, with a small set of numbers in 2 dimensions. Because the what is in 2 dimensions, you can see it, right? So there is a theorem which says that every matrix can be decomposed in this way. So this is n times r, this is r times r, this is r times p. Okay, so every matrix can be decomposed as the product of 3 matrices. What is the matrix U? U contains the eigenvectors of x prime. V contains the eigenvectors of x prime x. Gamma contains the eigenvalues of x prime x or x prime or xs prime. The eigenvalues are the same. The eigenvectors are different, but the non-zero eigenvalues of x prime or x prime x are the same. Right. It is clear that if you now do this trick, you divide it by square root of n minus 1. Here you have divided by n minus 1. And then in this case, you are the eigenvectors of x prime divided by n minus 1. This is divided by n minus 1, and this is divided by n minus 1. Therefore, it is clear that if you take the deviations from the means, this is what? This is the variance covariance matrix. Tell me. No, it is writing because I just put the, yes, it is right, yes. Yes, I just put the tilde. I just put the tilde on all the matrices. So, if therefore this V is the matrix of the eigenvectors of the covariance matrix, right? Therefore, this is something which is very general. Now, x tilde n times r, therefore can be written as these are U1, U2, U R, gamma, and these are V1, V2, V P. Well, let us say it is the transposed. It is transposed. Okay, so this is matrix N times P, can be written as the sum of Uj, gamma j, Vj prime. J which goes from 1 to P. So this is, well, given that the rank is R, so the sum goes up to R. So this is n times 1. This is 1 times 1, and this is 1 times P. So this is the sum of R matrices, each of size n times P. And the incredible thing is that these numbers, gamma j, are always positive. This is something incredible. In every matrix, you, independently of the numbers that the matrix contains, you do find certain numbers that are always positive. Incredible. Incredible. These numbers must be something magic. This is, but this theorem was completely unrelated to principal components. It was known as a theorem of linear algebra, completely disconnected to principal components. Just 40, 50 years ago, people realized that there was a connection with the principal components. So this is gamma. Gamma is, I said, the function of the eigenvalues are the square root of these eigenvalues here. Therefore, matrix gamma is the matrix which contains the square root of the eigenvalues of the covariance matrix. That is, gamma times gamma is equal to lambda. The diagonal matrix of the eigenvalues of the correlation of the covariance matrix, or of the correlation matrix if you start with matrix Z. Okay, so any matrix, this gamma contains the square root of the eigenvalues of the covariance matrix. Incredible. Now, yes, the square root of the eigenvalues of the covariance matrix. Right. Now, let us see more deeply. X tilde, so for U, gamma, V, transposed. Therefore, X times V, the principal component transformation that we have seen yesterday, because you do this transformation, you find this eigenvector is simply equal to U times gamma. Now, what is the covariance of X tilde V? Okay, we do it. V prime, X tilde prime, X tilde divided by n minus 1, V. Okay, this is the covariance. The covariance matrix means 0, and so you fully understand it, right? Okay, so this is V prime S V, right? So this is V prime, spectral decomposition of S. This is S, spectral decomposition of S. This V prime times V is the identity, V prime times V the identity, and then you have matrix lambda of the eigenvalues, right? So the principal components have a variance-covariance matrix which is a diagonal matrix because they are orthogonal, they are uncorrelated. The correlation coefficient between the first and principal component is 0. This is diagonal, and the diagonal elements are those of lambda, the eigenvalues. Or you write it as gamma, gamma star. Well, gamma, yes, gamma, gamma times gamma. So gamma contains the square root of the eigenvalues. The square root of the eigenvalues of the covariance matrix are called singular values. Right. Okay. Now we start from here. And we say, here we want to find, given this result, here we want to replace x tilde with another matrix, which is x hat. Another matrix of rank 2. An approximation of the original matrix, right? Rank 2, you can see it in 2 dimensions, right? And what is the condition? The condition is that the sum of the difference between the elements of x tilde and the elements of x hat is minimum. You want to minimize. You want that this matrix is as close as possible to the original matrix, but has lower rank. Oh, well, linear regression minimizes the sum of squares of the residual. It is the opposite of what we saw yesterday, that is the projection or the linear combination of the variables with the maximum variability. Here is another approach. The goal is to show that if you start with these 2 different approaches, you end up exactly with the same result. It's incredible. Because they have been proved, one has been proved 100 years ago, the other one has been proved 60 years ago, but the connection has appeared cleared just 50 years ago. That this approach will end up with the same approach as the other. So you can see this is, but how many unknowns there are? There are, here you want to minimize, to minimize with respect to x at ij. But there are n times p unknowns, because you have to replace the original matrix n times p numbers. It may seem unfeasible. Right. Now, if you have now a generic matrix X, how do you write in matrix algebra the sum of the squares of all the elements of X? How do you write these things with the sum? I goes from 1 to n, j goes from 1 to p, x, I, j square. Right? The sum of all the numbers, sum of squares of all the numbers of a matrix. How do you write it? So, the one who answers gets 1 extra point. How do you write it in matrix algebra? The sum of the squares. No, because that's a matrix. So you write it as the trace of x prime x. Or you write it as the trace of x prime. The same thing. Yes, and this is one of the exercises of chapter 2. because you take the trace, so you take the sum of squares of everything, you see. Okay, well, no, well, you can check it in MATLAB as you like. Therefore, this condition here is minimize the trace of x minus x tilde. Okay, let us write it this way. Okay, transpose x minus x tilde x hat, right? With respect to x hat. So you minimize the sum of squares of the difference. You see that, that there is minimize the trace, right? So, given that x hat, or given that x can be written as sum of u I gamma I v I transpose, I which goes from 1 to r. Okay, so if you take x hat as the sum I goes from 1 to 2 of u I gamma I v I transpose, the difference between the two is what? Is the sum from I which goes from 3 to r of ui gamma j ui gamma I vi prime. So this is the sum which goes from 1 to r. The other is the sum which goes from 1 to 2. The difference is the sum which goes from 3 to r. Okay. Therefore, the sum of I which goes from 3 to r of ui gamma I vi transpose, all this, okay, and then this is, so we have to write this thing here. Therefore, this thing is this transpose sum I which goes from 3 to r of ui gamma I vi prime. So this is exactly equal to this. Okay. Now we do the multiplication. So this is n times 1, 1 times 1, and this is 1 times p. Okay, sum I goes from 3 to r. This, I take the transpose here. Therefore, vi gamma I ui transpose. The transpose of the product. Okay? And this is the sum of I which goes from 3 to r of ui gamma j gamma I vi prime. The ui are the eigenvector of the eigenvectors are orthogonal. They form an orthogonal basis. Therefore, the product of ui, for example, 2 with the ui 3, with the u3 is 0. On the other end, the product of ui transpose ui is equal to 1. Because they are orthogonal, because the matrix is orthogonal. So therefore the matrix is such that u prime, u is equal to the identity. Or if you want, u times u prime is equal to the identity. Therefore, this difference, the trace, the sum of squares of the differences, therefore this becomes equal to 1. Then becomes sum for I is equal from 3 to r, I is equal from 3 to r, vi gamma I square VI transpose. Right? And this is still the trace here, the trace of this thing. The trace, in the trace, you can exchange the order. And so this is becomes gamma I square VI prime VI. Same thing about the VI. Okay? Same thing about the VI. Goes from 3 to R. So, therefore, all these things, these are equal to 1 when the index of the sum is the same, and is equal to 0 when the index of the sum is different. So therefore, this quantity is minimized and is equal to the sum of gamma j, gamma I from I, which goes from 3 to R. So sum of gamma I square, sum of lambda I which goes from 3 to R. Incredible. What remains is the sum of the eigenvalues of the covariance matrix. Exactly what we saw yesterday. Don't you think it's something exceptional, eh? Something exceptional. Something exceptional because if you understand, everything flows. There is nothing to remember. You just have to remember that the eigenvectors are orthogonal, is a matrix which is orthogonal, and that's it. That everything flows. Okay? So, here, it is clear, when this thing is minimized, the sum of squares of the difference is minimized in 2 dimensions if you take the first 2 largest eigenvalues of the covariance matrix, because what remains are the numbers which are the smallest possible numbers. You order the eigenvalues, and this is what remains. And it is incredible because this is a big sum, you know, you see, for all I, for all j. The difference is just the sum of the eigenvalues. Incredible. And there is an analytical solution. It's not a maximization or blind minimization with n times p unknown. No, everything is analytic. Incredible. Okay, therefore, this was the first slide. This was the first slide that we have seen, and then this is, you find it in the book, and this is the thing. Okay. First 2 eigenvalues of x prime x, but it goes without saying that if you divide it by n minus 1, there are the eigenvalues of the eigenvectors of the covariance matrix. How do you compute the singular value decomposition in MATLAB? Simply SVD. So it's something which is very, very... So, and then you obtain these 3 matrices here. And then, if you multiply these 3 matrices, you obtain the original matrix. Right. And so there is exercise 11.1, which is an implementation of this concept. You will have it, you will download also the solution. So the first exercise of chapter 11. Now we consider the third approach to principal components. The first was linear combination of the original variables. The second was find the best low rank approximation of your matrix. Now find the projection of the points. Now we let me It is recording, yes. Yes, you cannot expect that everything works perfectly. You have to relaunch it. So far we had the perspective of the variables. So far, we had the perspective of the variables, the x written as x1, x2, xp. N times 1, n times 1, n times 1. Now, we consider the rows. We consider the rows, and then we have x1 transpose, x2 transpose, xn transpose. So this is n times p. This is equal to n times p, the first row, n times 1 times p, the second row, and then 1 times p, the last row. Right. These are vectors in p dimensions. What you want to do? You want to project these vectors in p dimension in a let us say in two dimension. For example, you project into a straight line. You project into a low dimensional space, right? And what do you want to achieve? You want to achieve something which says that the difference between the x and the x hat is as small as possible. You want to have orthogonal projections in such a way that these distances are minimized, right? And so this is what you can understand it, that you minimize this thing, because you minimize these distances here. So you want to choose xi hat in such a way this thing is minimized. Okay, Pythagorean theorem, then, okay, this is the square norm of this is the square norm of this plus the square norm of this. This is yes, exactly. Yes, the Euclidean theorem. Okay, so you minimize this quantity here, which is as equivalent to minimize the difference between the square norm of this minus the square norm of this. Okay? Okay. When we repeat this quantity here, and now if you minimize this quantity, then you see that this is xi tilde are the points that you observe. You cannot do anything. It's the total variability of the points, right? You cannot do anything. But here there is minus this quantity, minimize minus this quantity, minimize minus, that is here you okay, so this thing here is equivalent to maximizing what? Is equivalent to maximizing this thing. Let me see. Minimizing this thing here, given that with this guy here you cannot do anything because this is the total variance. You cannot do anything here. So minimize minus is like maximizing this quantity. Now, to be sure, you understand this step, that this is equal to the sum of the variances. you can you see it? Or okay, those maybe you cannot see it. Tomorrow in the computing class we do the algebra. So if you minimize these lengths here, minimizing this thing or maximizing this is the same thing, right? So the closer is the smaller is this difference, the largest here is on the other dimension. So therefore here you maximize this thing, but x hat is what? X hat is what? This is the formula to compute x hat, but you project in vectors that are orthogonal. Therefore, here you don't have the denominator because v times transpose is equal to 1. So the length of the projection here is x prime y. So you maximize, therefore x hat, this thing here, is equal to this expression, to the scalar product. You see it? That you have to maximize this quantity, but x hat I, the length of the projection is what? Is x y prime times a. No, here there is not the triangle inequality. There is, well, you agree that you have to maximize this quantity? Let me see. This is the minimum of this thing. Here, the first, you cannot do anything. Here, you can act just on the things that you want to estimate. So, minimize xi at square, the norm. Minimize minus, that is maximize. Here it is. Minimize minus, that is maximize. Then x at I, the length of the projection is what? X at I is equal to, in general, if you project into a vector y, is the scalar product. Here it is the scalar product. You project it to A, and A is an orthogonal, is as norm 1. That's the reason why here you don't have the norm of A. Oh, well, actually, you have the norm of A, but the norm of A is equal to 1. So, this thing here, let me go. Lost again. Well, this is very fragile. Lost again. Okay, another mystery to me is why it starts with 3.5% and not with 100%. This is fully unclear to me. Okay. Where now? So we were here, maximize. Okay. So here, maximize x I tilde a, the sum square maximize with respect to a. Okay, now let me okay, maximize, then here we have the sum. Maximize the sum of the projected points. Now, this is maximize the sum of the projected points, therefore the norm, therefore this will be a prime xi tilde xi a sum I which goes from 1 to n. xi prime, right? So this is p times 1 and this is 1 times p. Therefore this is p times p. Okay, so what is this quantity? The sum of xi tilde xi prime. What is this quantity here? What is this quantity here may be divided by n minus 1. And we said that x tilde is equal to x1 prime, x2 prime, tilde, xn prime, tilde. Therefore, x tilde prime x tilde is equal to x1, x2, xn, x1 tilde transpose, x2 transpose, xn transpose. Okay? This is p times 1, p times 1, p times 1. 1 times p, 1 times p, and 1 times p. Therefore, this is, you multiply this for this one for the second, the nth for the nth. And so you have the sum of xi prime. Therefore, if you divide it by n minus 1, is what? Is the variance covariance matrix once again. Incredible, eh? Is the variance covariance matrix. Therefore, this sum here is maximizing a prime SA apart from the factor n minus 1. And this is exactly what we saw yesterday. Incredible. Incredible. So the sum of the distances is minimized, you end up with the same approach as we saw yesterday. But yesterday we started from the linear combination of the original variables, an approach which was completely different. In fact, Hotelling proved it 70 years ago, Pearson proved it in a completely different way, and then there was the singular value decomposition. So these genius persons had exactly proved the same thing. Incredible. You start from A, from B, from C, you end up with the same conclusions. Okay. So therefore, and this is what I write here. Now, in summary, in the transformation of principal components. If you start from Z or X tilde, you have to find this matrix of the eigenvectors of S or of R, of the correlation matrix. So you end up with this transformation of the Z matrix or of the X tilde matrix. Let us see now in practice. So here the points must be projected on a line. The projection must be orthogonal. So you have to find here, you have to find the equation of this line. Right. And this is the equation from this line depends on the first eigenvectors, the equation of the second line, of the perpendicular line, of the orthogonal second orthogonal line depends on the second eigenvector. Now, well, you have this set of points, you compute the covariance matrix, you compute the eigenvalues and eigenvectors. Okay? Now, what is, we are about to see, what is the geometrical interpretation of the eigenvalues? Now, let us see. What is, you know, there are two things that are orthogonal. What is the equation of the x-axis? Is y is equal to 0. If you have the coordinate system x, y, the equation of the x-axis is y is equal to 0. Y is equal to 0 in multivariate things that you want that this vector v2, the second orthogon, the vector v2, the direction of the second semi-axis, the axis of the ellipse is orthogonal to x. So you end up with this constraint here, and then you find the slope and the okay, of the straight line. And so you draw it. These are the things. So you find the first eigenvector, direction of the first principal component line. Okay, this file is called project. Therefore, if you go to chapter 11 and then you do the pool, because so that you have the most recent version of the file. Here you read this example, you compute the covariance matrix, and then first you do the plotting. Okay, you do the plot of the data. Then, second thing, well, in the past we added the confidence ellipses. Confidence ellipses, you add them with the function ellipse. Okay, this is, you compute the eigenvalues and eigenvectors, you sort them. Let me run this part. So you have lambda, the matrix of the eigenvalues, which is diagonal. And you have this V is the matrix of the eigenvectors. The matrix of the eigenvectors, which is orthogonal. Okay? V transpose V is equal to the identity. Now, principal line, exactly what we saw here, exactly the principal line. B' and A', they are here. And then you draw this line. Then you do the orthogonal projection. Let me tell you what you want to have. You want to have these points, that each point is projected onto the line. And the projection, you see, is orthogonal. Each point with the line forms an angle of degree 90. Right. Now, we need now go back, and then we need some algebra. Okay, so same decomposition that we are going to see this decomposition several times. So if you do x times v, you have y times gamma. Is it clear? Because v is orthogonal, eh? Right? Therefore, xv1 is equal to u1 gamma 1. Okay? So, x at, the best rank 1 approximation of x is equal to what? Is equal to u1 gamma 1 v1 transpose. This is the best rank 1 approximation, n times 1, and this is 1 times p, 1 times 1. X at is equal, given that u1 gamma 1 is equal to this, is equal to x v1 transpose. This is the best rank 1 approximation of your matrix X. This gives you the coordinate in the original space x at. Let us go to MATLAB. You see that therefore you have y1 is the coordinates of the projected points, but in one dimension. y1 times v1 prime, here, this is in 2 dimensions. In 2 dimensions. X at. But x at is what x at? X at. You see what is x at? You see that there are the coordinates of the line. It's incredible, eh? So this is the best rank 1 approximation of this 2-dimensional point. Can you see this is a rank 1 approximation? Because it's just a straight line. So you pass from 2 dimensions to 1 dimension. And this is equivalent to project the points, as you have seen. Okay? You project the points into the line. Orthogonal projection. And what is the code in order to obtain the orthogonal projection? You see that you have x at and then x1, x2. These are the original variables. Okay? You put them as n times 2, and then you take the transpose. Instead of plotting n times 2, you plot 2 times n. So you have the lines which connect each point. You see the trick? Right. That's the code. That's the code without any secret. And so this is the code which enables you to draw these projected points and to obtain this plot here. But what are the coordinates? These points, these coordinates are of x at. The best rank 1 approximation of your 2-dimensional points. And the algebra done in this way has no secrets. And is something that you enjoy. Because here there is nothing hidden. You see the theory, you see the code, and this closes the circle. So this is, yes, exactly this one here. X at. These are the best rank 1 approximation. Then, what is, now these are the residuals. These are the residuals. The difference between x and x at. Because what you have is, so here, these are advertising expenditure and the revenue the first two columns are the original variables. X hat is the best rank 1 approximation. Note that here you had removed the means, then you put the means back again. This is just a translation. Right. What is the sum of squares? What is the, then we have to do 95 minus 94 square plus 191 minus 191 122 square. Here, the sum of squares of the differences of all these terms. Because the closer, the better. What is this residual sum of squares? You see, what is, you have x and you have x, y, hat, and then you take the residual sum of squares divided by n minus 1. Well, the residual sum of squares divided by n minus 1 is the second eigenvalue. As we have proved before, look at this magic number. This eigenvalue is nothing but a function of the residual sum of squares. What remains is the variance unexplained, because you project points from 2 dimension to 1 dimension. This is exceptional, And then with just a number that is pre-computed, lambda 2, this is the residual sum of squares divided by n minus 1. Residual sum of squares divided by n minus 1. And you can see the notation of the trace, the sum of the squares of the elements, the sum of the square of the differences. Right. And this is, you find here, and this is the code. Project. And this is the thing, residual, and this thing here, and this thing here, and if you go back now to the matrix of the eigenvalues here, and it is this number, the second eigenvalue. So what remains of the sum of squares of the residuals is the second eigenvalue. And this shows how you have passed from dimension 2 to dimension 1. You have done orthogonal projection, and the sum of squares of the residuals of this orthogonal projection is just the second eigenvalue, apart from the factor n minus 1. Now, this is, if you look at the difference with respect to regression. In regression, you minimize the sum of squares of the vertical distances, right? Here, on the other end, you have the sum of squares of the projected distances, of the orthogonal projection. The line is different, Okay, now, principal components as rotation of the Cartesian axis. So this equation, the equation here, is just the equation of the ellipse. But this is the equation of the ellipse that, first of all, is not centered around 0. You know, there are the means. It's centered around the arithmetic means. And then the ellipse is different from the ellipse that I had always seen in my high school, because the ellipse that I had seen was the canonical ellipse, the ellipse which passes through the axis. It was not the ellipse which was rotated, of course. To small children you cannot say anything about the eigenvalues. So therefore, here we need to recall what was in chapter 10. In chapter 10, we saw how to transform a set of coordinates into a polyshaped object, compute the area numerically, find the intersection of a line. And this is file polygons intro. Polygons intro. If you have this file, then you load the data, you compute the ellipse, and then you transform into a polyshape, you compute numerically the area of the ellipse, you compute the perimeter in a completely numerical way, you compute the centroid, and then you compute the here numerically the points inside and outside. That was a file of chapter 10. Now we want to compute, and then you remember that in chapter 10 here the equation of the line which passed through to the major axis of the ellipses was given in a blind way. Now we have seen how to compute it. Now we know many more things. And so these numbers, they come from the matrix of the eigenvectors. Okay. So there is a file which is called rotation in chapter 11. This file starts with load, because here we start with a lot of variables already pre-computed. So this is, now there is, okay, let me close all, clear all. Okay, there is nothing in the workspace. Here we already have the coordinate of the ellipses, and then this matrix already loaded and everything. Right. So points in the original space with the ellipse, and now we want to compute the length of the major axis of the ellipse. Right? We want to compute it numerically and theoretically. Right? Okay, numerically, how do? You convert the ellipse in a polygon, then you take the intersection with the principal line, you take the norm, and then you do it numerically. 11.4681, everything is numeric. Here there is nothing. There is, the length, it is the norm. The length you do intersect, and then the points that is still inside, but the boundary with the ellipse, with the centroid. The Euclidean distance, that's the length of the semi-axis, numerically. Now, the length of the major semi-axis, now you do the square root of lambda 1, exactly the same number. It's something magic, eh? So, the square root of the eigenvalues, that is the singular values, these numbers which are just positive, and that's the reason why they are positive, because they are the lengths of the semi-axis of the ellipse. Isn't something incredible? Any matrix can be represented by an ellipse. This ellipse has a semi-axis, and the length of the semi-axis are the singular values. Incredible. Then this is the area perimeter calculated numerically, and then this is the area and the perimeter. This is with the exact formula, which is the formula of the ellipse, is pi gamma 1 gamma 2. So the area of the ellipses is the product of these two singular values multiplied by pi. But isn't something incredible? The area of an ellipse is the product of these two singular values multiplied by pi. But why pi? Why the singular value? We live in a world which is a mathematical world. And this is something that, it's incredible. Our universe is a mathematical universe. But why pi on Earth? Why this number? 3.14, why? Who knows why? One day maybe we will know. But certainly is something which is absolutely mysterious. You can prove it is this way, but it is something which is mysterious in our life. Mysterious, but challenging and fascinating. At least it has I mean, I'm fascinated by all these things. Now, what you do? Let us go. So therefore, the length or square root of the first eigenvalue is the first principal semi-axis of the ellipse. Okay, this is the thing. Therefore, this is the direction of the major semi-axis. The slope is 0.82 divided by 0.56. This is the slope, right? And look that if you change the sign of both, because if V1 is an eigenvector, minus V1 is an eigenvector, the ratio minus remains the same. That is, the slope remains the same. Isn't it incredible? And here you have minus plus, so it's the orthogonal. You change the sign, then the ratio remains the same. Okay. Then, okay, mathematical details are that, okay, then the, well, once again, so the variance of the first principal components, in this case, the standard deviation of the first principal components is this first singular value, is gamma 1, yes. Okay, is exactly the first singular value, the square root of the eigenvalue of the covariance matrix, of the first eigenvalue of the covariance matrix. Now, first, what we did was a dimension reduction from 2 to 1 dimension. If we take both dimensions, and this is the original one, and this in terms of the where the mean is 0. You can see that it's centered around the means. Here you have removed the means here. You see, this was centered around the means, and this is on the other end centered around 0, deviation from the means. And this is the equation of the ellipse. And there is this variance covariance matrix inverse. When you do this transformation, what you do, the ellipse, which was rotated, now becomes the canonical ellipse. And this is the equation of the canonical ellipse. And now you recognize that the length here is the square root of lambda 1, because the ellipse has been rotated, translated, and rotated. You see these magic numbers, but the length here, when you rotate, this length here does not change. It's just a rotation of the ellipse, okay? Does not change. And this is now the points which are outside here are the points which are outside here, and the points which are outside here. And what happens if you, okay, so this is the algebra. So, once again, the spectral decomposition of the matrix. Spectral decomposition of the matrix, right? So is s to the minus 1. The rules of s to the minus 1. So if a, b, c to the minus 1, c to the minus 1 times b to the minus 1 times a to the minus 1. And here you end up with this equation, the equation of the ellipse that you have always seen. With the eigenvalues, so the numbers down here at the bottom are the eigenvalues, of the covariance matrix, and the square root of the eigenvalues are the singular values. Incredible. So if you divide it by the square root of the eigenvalues, and then you end up with the circle. So the variance covariance matrix of the standardized principal components is the identity matrix. So, therefore, the summary is that in principal component you do this transformation or this transformation. If you do this transformation, you end up with the new matrix, which is diagonal. Otherwise, if you standardize, if you scale this, if you divide it by the square root of the eigenvalues, you end up with the covariance matrix, which is the identity. And once again, this is xvj, is the coordinate of the projected points. On the other end, this quantity here contains the coordinates in the original space. You see the best rank 2 approximation that we have seen, the best rank, rank 2 approximation. So with this transformation, you end up, you maximize the total variance, you have the best k-dimensional subspace, you have variables which are uncorrelated, and now let us see a practical example. This I want you to do in my final 20 minutes. So you have the Cities Italy data set. You start with the correlation matrix. And as you can see, there is a high correlation, for example, between added values and deposit, and also added values and pensions, right? When you do this transformation, you end up with, this is the covariance matrix of the principal components, okay? Which is, well, here there is still the Italian. Please, let me correct in the exercises if some Italian has remained. Every time you find something in the exercises written in Italian, please write in GitHub. Help me improve the files, because of course some Italian maybe has remained. Who knows? Could be. So, what is this? This is the variance of the first principal component. And this is the sum of the elements of the main diagonal is what? Is what? Tell me, Heidi, what is the sum?
No, I was going to say the trace.
Yes, the trace, but yeah, but the trace, yes, the trace, the sum of the elements of the mean, the sum of the eigenvalues is what? Here, how many variables you have? 7. So the total variance is what? 7, because the variables are standardized and then each variable is equal to 7. So the sum of the eigenvalues, here the sum of these numbers is 7. What is the proportion of variance explained by the first eigenvector? 3.3735 divided by 7. That is 53%. Multiply, okay, and this is the cumulative percentage. Therefore, the first two principal components, that is, if you pass from a data set of dimension 7 to a data set of dimension 2, first two principal components, you lose just 25% of variance. Right. It's just the eigenvalues who make the game. And then this is the Pareto chart. The Pareto chart, and then how many components to retain is something that we are going to see later. Now, how do you interpret the components? This is something that cannot be automized, because it is something that requires the fact of having understood. So you have these two new variables, the first two principal components. They explain 75% of the original variability. How on earth do you interpret them? You have to check the correlation between each component and the original variables, right? In order to understand what are these things, in order to interpret them. And what is the covariance matrix between the original variables, or the covariance matrix between x tilde and y? And this is, you can easily find this formula here. This is the covariance between the original variables and the principal components. This is the covariance. Covariance, you need the variables. The correlation is the covariance divided by the square root of the product of the variances. So here you have to divide by the square root. You have to divide by the square root of the variances. Therefore, square root of lambda j. You divide by square root of lambda j, and so you have lambda j divided square root of lambda j becomes square root of lambda j, right? Then you have to divide also by the variances of x, of the original variables. But if the original variables are standardized, their variance is equal to 1. So, in summary, the matrix which contains the correlation between the original variables and the principal components is called Loading's matrix. Let us see now, let us go to MATLAB and let us see the code. So, you loaded the data. Okay, this is data loading. Can you see? This is, you compute the correlation matrix. You see the code, the correlation matrix, okay? Nothing hidden, very, very simple. Then, you compute the eigenvalue and the eigenvectors, okay? Then you have this matrix of the eigenvalues and the matrix of the eigenvectors. Then you compute the score, transformation Z times V. Okay, this is a new matrix. So Y is the matrix of principal components. The covariance matrix of Y is what? Lambda, the matrix of the eigenvalues, right? What is the trace of this matrix? What is the trace of this matrix? What is the sum of the eigenvalues? 7. Right. Pareto chart of explain, then you do this, then you create this table, you see. This you create this table. Okay, with these 3 columns, everything is very, very easy. Then Pareto chart of explained variance. Run, and that's it. This is the Pareto chart. The first 2 explained about 75% of the total variance. Then interpretation. You compute the matrix of loadings. V times the square root of lambda. V times the square root of lambda. This is the matrix of loadings, of the correlations. V times the square root of lambda. V times the square root of lambda, and this is the correlation. Therefore, this implies that the first principal component is correlated strongly and negative with added value. Is correlated strongly and negative with the amount of deposits, right? Is correlated strongly with pensions. These are indicators of money, added value, deposits, now the amount of money which is in that particular province. And then is correlated negatively with export. So therefore, higher value of the first principal component imply small values of added values, small deposits, small pensions, high unemployment, because this is directly correlated. And then implies low export, and then with bankruptcy, this has nothing to do because the correlation is very small, but high bills overdue. So when you try to trick the cards that you don't pay the bills. So a province which has high values of the first principal component is a province which is really very, very poor. Can you see it? Vice versa, a province which has very small values of the first principal component is a province which has high added values, high deposit, high pension, small unemployment, and high export, and small bills overdue. Second principal component. The second principal component is mainly correlated with bankruptcy and bills overdue. Therefore, high values of the second principal components are provinces that have high bankruptcy and high bills overdue. Are provinces that are really, whose firms behave really in a very bad way. And that's the interpretation. Right. Now, these numbers now can be plotted in this way. The correlation with the first principal component and the correlation with the second principal component. You see that unemployment bills overdue positive and the others negative. The plot is also very effective. And the correlation with the second principal components. Then, okay, now we see this matrix of the loadings. This matrix of the loadings, this is V square root of lambda. Therefore, the first column of the loadings is V1, first eigenvectors, times square root of lambda. Right. Because in general form it is V times square root the matrix of all the lambda. In general, the first is V1 times lambda, square root of lambda 1, correlation with the first principal component, correlation with the art principal component, you take the art eigenvector and the square root of the art eigenvalue. So these are the correlation. Okay, now, so how do you interpret the first principal component? A variable that has a negative related with added value, with the positive, with the pension, and then is positively correlated with unemployment. And also, unfortunately, here they can remain. Okay, so this is really a poverty indicator. This is an indicator of poverty. The larger, the more poor is the province. Second principal component is a sort of this malaise index because it is strongly correlated with failures, with bankruptcy, with bills overdue. Now, what is the sum of squares of all these elements? No, the sum of squares. Minus 0.96 squares plus minus 0.89 square is what? Exactly. The sum of the squares is not the singular value, is the eigenvalue. The square of the singular value, right? Why? Because these are V times square root of the eigenvalue. If you take the sum of squares, V times V prime V is equal to 1. You square the eigenvalue. And so it is the eigenvalue here. Now, let us see the algebra. It is... no, that was my dream that everything could still work. Right. So, this column, the matrix of the loadings, is this thing here, the first column. Right? the sum of squares of the first column, the sum of the square is this, of this vector, eh? And now you have V1, lambda 1 is equal to lambda 1, because this is orthogonal. So the sum of the squares is equal to, the sum of squares of the first column is the first eigenvalue. The sum of the squares of the rth column is the rth eigenvalue. Then, what do we have? So, in the loadings matrix, the sum of the squares of each column is given by the corresponding eigenvalue. On the other end, the sum of the squares of each row, the correlation, if you square the correlation, is what? Is the R square, the variance explained. So you take, if you sum the squares, for example, here of the first row, this is so-called communality. That is the proportion of variability of the variable, which is explained by the first two principal components. You see the interpretation, eh? The variables are orthogonal, and therefore the R square sum up. Because in the regression, if you add an orthogonal variable, then the coefficient do not change. If you add another variable which is orthogonal, eh? So the sum of the squares of each row is the communality of the particular variable. So these are the communality. How is it obtained? 0.91. It is obtained as minus 0.96 square plus 0.04 square. And then you obtain this number. This is the communality. So the variable which is better explained, in this case, is added value. Now, you plot the correlation between the variables and the components. This is the plot of the correlation. This is the plot of this matrix here. Eh? But one thing is to see the numbers. The other thing is to see this plot. And now, do you remember the interpretation of the correlation coefficient and the angle between vectors? That is, if two vectors have a very small angle, means that the correlation is high. If the two vectors have a degree which is roughly 90 degrees, the variables are orthogonal. If the variables have an angle which is around 180 degrees, they have a strong inverse correlation. Therefore, all these variables, you see that the arrows, then the direction of the arrows is on the left, therefore they are negatively correlated with the first principal components, because they go in a different direction. Not in the unemployment goes in the direction of the first principal component. It is correlated positively with the first principal component. And now look at the angle between deposits and then the added value. They have very small angles, so they are positively correlated. So this group of variables shows a positive correlation because their angle is very small. And then this variable has a correlation which is roughly 0 with bankruptcy, because their angle is roughly 90 degrees. On the other hand, unemployment and added value, they are on two different directions. They are correlated strongly, but negatively. So you see? Now, what is the variable which is mostly correlated with the second principal component? Which of these? Which is the variable which is strongly correlated with the second principal component? Bankruptcy. Clear, because the angle is very, very small. And positively correlated, because the direction goes in the direction of the axis. So, you see the power of principal components. Here in 2 dimensions, you have been able to show a plot that only God can see in 7 dimensions. Incredible, eh? Here in 2 dimensions, a human has been able to see all the main facts. Now the scores. The scores are when you have this z times v, because these were the variables, the correlations. But then you have the position of the units. These are called the scores. The scores can be standardized or not standardized. Now, let me show the scores. The scores, this is the first principal component. As you move from left to right, the province becomes poorer and poorer. As you move from bottom to up, the business malaise index increases. So the worst town in Italy are those which are located here. The best towns in Italy are those which are located here. Right, now, of course, there is a big overlap, and then there is the B-plot which combines the two things. Now I show you everything in MATLAB. Okay, clear? GLC. Then you do load cities Italy. Okay? PCA-FS cities Italy. 2 lines of code. 2 lines of code. And everything will be done. Everything will be fully done. Everything will be done because you will have figure 1, the variance explained by the components. You will have figure 2, the correlation between variables and component. You have then the explained, the explained variance, the loaded, then the outlier map, we are going to see it later. And then you have an interactive biplot, B-plot or biplot. Well, this is short points. This is the thing that we are seeing, the matrix of the loadings, right? And then the angle that we have commented before. Okay, then here you say, I also wanted to show the row names. And then you see, text density percentage. Here we are able to control the percentages of the labels. You see, we control the percentages of the labels. This is FSTA, that we are the top all over the world. I mean, this is, don't tell us anything because we are the best programmers and then we can do everything. So, show row names, then, well, you can put a confidence ellipse, then we are going to see it later. Then remember that this is a poverty index. As you move from left to right, the poverty of the province increases. But people wants to see the opposite, wants to revert the sign. Because the first eigenvectors, I can change the sign. Instead of having a poverty index, I can have a wealth index. And then change the sign panel. And then change the sign of the first principal component. In this case, it is the opposite. Now, the first principal component is positively correlated with the positive variables, and vice versa. Okay, and this is what our newspapers do. That is the rank of the provinces using the first principal component. That is our financial newspaper, which is called Il Sole 24 Ore, that every year publish the ranks of the Italian provinces using the first principal component. Then you will have then, given that these points are projected, then there is a orthogonal distance to the subspace, but we are going to see it during the next meeting. So you have a color which is proportional to the orthogonal distance. Now, let me say that when you call PCFS, automatically in the command window, it gives you everything automatically, unless you decide that you want to suppress the output. So you see the loadings, the commonalities, everything. And then in out, if you do this thing out is equal, then you find everything in variable out. So this is a struct. Therefore, for example, out dot r table is the correlation matrix. R dot, for example, loadings t is the table. Out dot loadings t is the loadings matrix, the matrix of the correlation between the variable and the principal components. Out dot, and then here you see the loadings, the orthogonal distance, and the commonalities. Commonalities, right. The commonality with respect to the first principal component, the second, and the total commonality. This first column is the square of the correlation of the matrix of the loading, the square of the second column, and then the sum. Therefore, added variable, the variability of added variable is explained mainly by the first principal component. You see added value as an angle which is very, very small with the first principal component, but which is almost orthogonal with the second principal component. So the variability explained by the second principal component is very poor. So that is to say, the overall commonality is 91.9, but its variability is fully explained by the first principal component and not by the second. Well, I really wanted to tell you many more things, and then my regret is that I start now, I will tell this A, B, and C. I'm just able, after 1 hour and a half, to tell you 20% of the things that I would have liked to tell you. But anyway, that's life. We are human. Thank you very much. So see you tomorrow morning.